My name is Earlence, and I'm here to talk about how IoT developers can build applications that better respect the sensitivity of the data they work with. This is joint work with my colleagues at the University of Michigan and at the University of Padova. Amir, my co-author, and I will be on the job market soon, so you might want to. Okay, so the IoT has several application frameworks, several application domains, including wearables, connected healthcare, and smart homes. And all of these application domains produce a lot of sensitive information related to a person's activities, and even a person's family members. Furthermore, we're seeing an emergence of several third-party application frameworks that enable developers to build applications that compute on all of this sensitive data. Google Brillo and Weave, Samsung SmartThings, and Apple HomeKit are a few examples. So here is a quick example of one such app that you could build. This app accesses an IP camera that takes images of people's faces at a door, and then it performs face recognition, which you have heard a lot about today. And then if that face is authorized, it will go ahead and unlock a door. This app also provides a feature for the homeowner to basically check the status of the door from the internet. So more generically, we have this publisher of sensitive data that accesses a sensitive source, and it makes this data available to a consumer app that eventually talks to various sinks. Now clearly this app needs access to this sensitive data for its core functionality. It's a useful app, but it also has the potential to leak this data. Some of my past work has shown how this might be possible. So this brings us to the central research question here. How can we build applications that compute on all of the sensitive data in the IoT while mitigating data abuse? Now on the surface, this may not seem like a new question. It may not even seem fundamental to the IoT. So let's see whether we can apply existing techniques to solve this problem. So we went and we studied 3 existing application frameworks, and we found that all of these frameworks only support permission-based access control as the core mechanism protecting their data. We looked at the Samsung SmartThings API, the Google Fit API, and even the Android Sensor API. An example of a permission is like capability.log codes in the SmartThings platform, and this basically governs whether an application has the right to read pin codes. So now permissions are good at controlling what data an app can access, but they do not control how applications use this data once an app has access. What we really need is a form of flow control, information flow control. So let's see whether we can apply existing flow analysis techniques. So generally we see 2 kinds of the instruction level type. We see dynamic taint tracking, which has the advantage of being fine-grained and not requiring developer effort. But they often have higher computational overhead. They may need special hardware for acceleration. And attackers could use implicit flows to leak information. Often some techniques leverage specific language or operating system structures to provide the security guarantees. The second type is static taint tracking techniques that alleviate some of the computational overheads of the dynamic techniques. And these are also fine-grained, do not require any developer effort. However, implicit flows, IPC and asynchronous code can lead to leakages. Now there are also IoT-specific challenges here. So many IoT devices, including the hubs, are generally very simple hardware, very constrained hardware. There's also a lot of OS and language diversity that supports this whole idea of rapid application development, where developers use existing tools and technologies to quickly build apps. And finally, we see that a lot of IoT apps have a lot of asynchronous code due to physical device delays, as well as the whole fundamental trigger action nature of these applications. So therefore, we built FlowFence, a system where flow control is a first-class primitive, and FlowFence is specifically geared towards the IoT application consumer domain, and it solves IoT-specific challenges. It builds on research from 2 areas, similar to label-based flow control techniques. It tracks information at the component level and enforces flows through label policies. And similar to language-based flow control techniques, it requires a developer to restructure their applications to obey these flow rules, to make control and data flows explicit in app structure. And then it also requires developers to declare these flows, while FlowFence automatically prevents all of the undeclared flows. And so this leads to a flexible system that supports diverse publishers and consumers of policy, of data with the associated flow policies. And it also leads to a system that allows the use of existing languages, tools, and operating systems. For example, a FlowFence implementation at most requires the ubiquitous virtual memory and secure IPC from the underlying operating system. So FlowFence provides its security guarantees using two primitives, quarantined modules and opaque handles. I'll explain these with the help of an example. So consider some code that wants to compute feature vectors from a bitmap of a face. Currently, a programmer would simply write a function or set of functions that has the rights to access this sensitive data, and then it would return the feature set to the caller. So now, on FlowFence, the programmer would write a similar function, but he would have to submit this function to run as a quarantine module that executes in a FlowFence provided sandbox. All data on FlowFence is taint labeled, so in this case, taint_bitmap, and all of this data is only available within these FlowFence sandboxes that carefully control how information flows into and out of an associated quarantine module. When the time comes for such a module to return the results of the computation to a caller, FlowFence will intercept that return value and replace it with an opaque handle. So an opaque handle refers to the sensitive data, but it has several interesting properties. The most important is that it only refers to the data, but outside a QM, you cannot dereference an opaque handle. The only way you can get the raw data that an opaque handle refers to is by submitting a QM for execution in one of FlowFence's sandboxes. A quarantine module could also try to do a declassification to achieve useful work. And the only way to do this on this framework is to use a trusted sink that FlowFence provides. So the trusted sinks basically read the taint labels off of the caller and then look up a flow policy and then basically decide whether a declassification is allowed or not. So let's see how all of this works in practice. So we have our running face recognition app example, and we have a main program that basically calls a module to compute feature vectors. This accesses an IP camera, essentially a bitmap, computes features, and then sends it back to the main program. The main program then uses another module to called report and recognize that takes the features as input. It also accesses the state of the door, and then assuming this face is authorized, it will go ahead and unlock this door. Similarly, it updates the status of the door to an internet website for a user. Now, as I said, such an app can easily steal this sensitive information. So at this point, what flows do you think we need to allow on this application so that it functions properly but cannot leak data arbitrarily? So it's very straightforward to see from the structure. We want a flow from the door state to the internet, and another flow from the door state and the camera to the door controller. So FlowFence allows developers to create and isolate these flows directly in the structure of the app. So let's see how that happens. And yeah, so we do not want we want to prevent the flow from the app to leak the bitmap. So the refactored app, we have a main program that is not a QM, and it goes again and it calls a module to compute features, but this is a quarantine module running in one of our sandboxes. This module will access sensitive data. In this case, this DC refers to the data of the camera, and since all data is taint labeled, TC is the taint label of that camera data. When it does this access, it gets the sandbox running, the QM is labeled with that same taint label. So now QM features has computed its vectors, and when it does a return, as I said, FlowFence is going to intercept that return value and convert it into this opaque handle, which basically refers to the transformation of the input data. So H1 is the opaque handle. So now the only useful thing this app, the main program, the non-QM code can do with this handle is to simply send it to another QM, because outside a QM, a handle does not, it is not the raw sensitive data. So here it sends it to another recognizer QM. This QM also accesses the door state data labeled differently. And now since this QM has accessed data from two different kinds of sources, the taint labels on the sandbox running that particular QM basically reflect that it has accessed camera data and door state data. Now again, assuming this face is recognized, it's going to try to do a declassification to the door controller. So the app will use one of FlowFence's trusted APIs to do this. But before the trusted API allows the declassification to succeed, it's going to basically read the taint labels off of the collar and then look up flow policies that I've shown in red here. So the flow policy basically says that the camera data and the door state data can basically flow to the door actuator. So in this case, this flow will be allowed to go through. Similarly, we have another quarantine module, QM report, that simply reads the status of the door and declassifies that to the internet, and we have a corresponding flow policy that allows this. Now, this app could try to basically leak this opaque handle. The non-QM code could try to do this, but this is of no value to the attacker because it is not the sensitive data. This app could also try to, just try to leak the camera data to the internet, but there is no flow policy that allows such a flow. Therefore, that is also going to be denied. So in this way, a developer can basically restructure his app to better respect the sensitivity of all of the IoT data it's working with, and in this way, we can create and isolate flows. So let me go into a little more detail on the design of these labels and the flow policies. So as I said, an opaque handle is associated with a set of taint labels, and each of these taint labels is a tuple of the form an application identifier and a label name. So this application identifier is unique on the underlying operating system, and the label name is simply a well-known string that describes the type of data. So since we use Android as our implementation platform, we simply use package names as the application identifier. So here com.camera.publisher is one example, and the label name is taint_camera. So now the policy is simply a set of flow rules. Each flow rule is of the form taint label flows to sync. So here we have two flow rules that allow camera data to go to the UI and heart rate data to go to the internet. So building on this label design, we come up with the idea of publisher and consumer flow policies to better support practical IoT apps. So a publisher policy gives publishers of sensitive data, such as a heart rate monitor, a chance to express legal uses of all of its data. So in this example, it allows the flow of D1 to S2 and D1 to S1. But in practice, it's difficult for a publisher to predict all uses of its data in advance. So we also introduced the notion of a discretionary style consumer policy that basically gives a consumer a chance to request intended data flows. So in this case, it wants to send D1 to S3 and D1 to S1. So at this point, we have like conflicting policies, right? How does FlowFence reconcile these two policies to get a single policy that we can apply to any given app? So we do this using a two-stage process. First, we simply compute an intersection of the publisher and the consumer policy, and any intersecting rules are basically applied for that app. And then we compute a difference between consumer policy and the publisher policy, and any difference rules will be surfaced as a flow request to the user. So at this point, a user has to decide whether to approve or deny a particular flow request. So to round out our running example, here is the policy set for our face recognition example. So the publisher only allows that, okay, the app can show the camera data to the user via the UI, and the consumer needs the three flows of the camera to the door controller, door state to the door controller, and door state to the internet. So in this case, the user would be prompted to approve or deny all of these three flows. And the final piece we need for a practical, secure IoT framework for these applications is some data sharing mechanism between publishers and consumers. So we distilled three key properties we need to support from our framework study. The first one is a simple polling interface where applications simply check publishers for new data. Similarly, a callback interface where an application is given a callback. Now, these are fairly obvious, fairly standard, very well-known patterns. We also found a third pattern, which is device independence. So consider an example heart rate monitor device. There are several kinds of devices of this type, and all of them produce the same kind of heartbeat data. So ideally, consumers should only need to specify what data they want without specifying how. So this would involve, they don't need to specify details like BLE connections and Z-wave pairings and all of that. So FlowFence supports these three properties using two mechanisms securely. So the first is a key value store that supports the polling interface. So here, each app on FlowFence gets its own KV store, making it the owner for that store. And then each owner is allowed to write to its own KV store, but there is no restriction on where an app can read from. And finally, fundamentally, keys are public information because they have to be already, like the consumer should already know about a key if a publisher and consumer are to talk to each other. So let's look at an example. We have QM1 here that has some sensitive data T1. And then we have a key called cam_bitmap. So when this QM wants to publish data, it simply does a write specifying the name of the key. This data goes into the KV store and also the taint label. And later on, when QM2 wants to read some sensitive data, this may be from another app, it will simply issue a read specifying the name of the key. And then it will automatically inherit the taint label and it will receive the data in return. Now, since the key is public information, we must ensure it's not affected by sensitive data. Therefore, we require that this key is created outside a QM where there is no sensitive data. So this is to prevent publishers and consumers from trying to exchange data by stripping off taints. The second mechanism is called event channels, and this supports the callback interface. So here, applications can declare statically at install time a set of channels that they want, making that app the owner for all of these channels. Similar to KV stores, only the owner can fire an event on any given channel it owns. And again, this channel name has to be public information, fundamentally because publishers and consumers need to know about the name of the channel if they are to communicate. So another quick example, we have our same QM1 that has some sensitive data labeled T1. And then we have a subscriber QM that can issue a subscribe call by specifying the public name of the channel, and then it can name a QM for callback. So then later on, QM1 can issue a fire event specifying the name of the channel, and this results in this data flowing through the channel and being delivered to the QM2, and the taint label will automatically be inherited by QM2. We support multiple such channels, and multiple subscribers can be on a single channel. As before, the name has to be created outside a QM to ensure that it is not influenced by sensitive data, because there is no sensitive data outside a QM. So in terms of implementation, generally today, we see two kinds of IoT architectures. We see like a cloud-first architecture, and we see a hub-first architecture. We focus on the hub-first architecture due to its robustness and its popularity. Therefore, we simply use an Android phone as our hub, and we have written some bridge code to interface with the SmartThings platform and the Google Fit platform so that we can run real IoT applications. So in terms of implementation architecture, our applications are simply regular Android apps bundled with code and resources. And the trusted service runs in its own context, and it maintains the opaque handle table, which is basically the mapping between raw data values and the handles. And the sandboxes use the isolated process feature of Android that controls the channels through which information enters and exits the process. This also supports native code, a property which we use in our later evaluation. So in terms of evaluation, we looked at this system from three perspectives. From a micro level, we looked at computational and memory overhead. We studied memory overhead, QM call latency, and data transfer bandwidth into the sandbox. And we find that all of these overheads are reasonable given our cyber-physical application domain. For example, call latency of 92 milliseconds is comparable to IoT device operations over a wide area network. And this, our bandwidth basically can easily accommodate the peak bandwidth of a typical IP camera. The second question is, can we support now real apps in a functional and secure way? And to show this, we ported 3 existing IoT applications to this framework, and we found that it requires adding less than 140 lines of code per app, and we found that it was fairly straightforward to basically create and isolate these flows. And finally, we also looked at macro performance factors for throughput and end-to-end latency for critical operations on these apps. So I'm just going to focus on these two. Please see the paper for details on the micro benchmarks. So the first app we ported is a smart lights app. It basically monitors a beacon around a geofence that is around the home. And if this beacon enters the geofence, it basically activates lights around the home. The only flow we needed to authorize for this app was to flow location to switch. And the data security risk was that this app can leak location information because it has access to the geofence and the location beacons. The second one, as you know by now, FaceDoor is our face recognition application. It can leak images of people, and we require the 3 flows to ensure that it is functional and secure. And finally, we looked at a heart rate monitor application that measures heartbeats using the camera. And the security risk here is that it can leak these images and this heart rate information. And since the only function of this app is to compute the heart rate and show it to the user, the only flow it really needs is to take the camera data and show it to the UI. So in terms of effort, we ported the first 2 apps in 2 days of effort each, and the heart rate monitor took a single day of porting effort. These are standard work days, and it was done by a person who was just introduced to the FlowFence API. Finally, in terms of the macro performance factors, we studied end-roll latency for FaceDoor, which we define as the time the app is given a bitmap until the time it computes these feature vectors. And we see approximately 100 milliseconds increase in latency due to the QM call latency as well as the inter-process transfers. We also looked at recognition latency, which is the time the app is given feature vectors and then it does a matching in a database. And on average, we see a very reasonable increase in latency. And this does not cause user noticeable delays in actually recognizing a face and then going and physically actuating a door lock. We also studied end-to-end latency for smart lights. And so this is defined as the time a location beacon enters a geofence till the time the lights are actually turned on or off. And again, 100 millisecond approximate increase. And this, of course, does not cause user noticeable delays because a person has to physically walk through the geofence and open the door, and by the time the lights are already on. And finally, we looked at throughput for the heart rate monitor app, measured in frames per second. And we observe a very slight decrease in throughput, but this does not affect the ability of this app to compute the heartbeat data and display it to the user. So in summary, several emerging IoT frameworks enable third-party developers to build applications, but they only support permission-based access control. And this can lead to malicious apps that steal this sensitive data easily. We built FlowFence, a system that embeds control and data flows directly within application structure. And developers must split their apps into 2 logical pieces, a set of communicating quarantine modules that exchange information with each other through these taint-tracked opaque references. And then the other logical piece is non-sensitive code, executes outside QMs, and it just orchestrates QMs to achieve useful work. We introduced the notion of publisher and consumer policies for these IoT apps, and we find that such policies lend themselves well to building practical IoT apps. We ported 3 existing IoT apps in 5 days. Each required adding less than 140 lines of code per app. And finally, macro performance tests indicate that the overheads are reasonable given our cyber-physical application domain. Thank you. I'll take questions.
Thank you.
So basically, in this approach, the developer of the application need to embed these policies, right? So what happens is, what happens if the developer does not to want to basically put these flow policies inside and tries to leak some information.
So, I mean, the assumption here is that the only way to write the application would be to use FlowFences, to use FlowFence. Like, think of it as like writing against an API, right? Like you write applications against the Android API, and you have to do that. There's no other way to write an application. And here you have to write an application against the FlowFence API.
So that will be the only option?
Yes.
Okay.
Yes.
Thanks.
So can you comment maybe also on the integration? So what you see is that developers would from the beginning develop apps with having FlowFence in mind, so putting it directly, or taking the retrospective perspective of like putting it as you did and then like uploading a second version for
so our vision is that developers directly write applications for a FlowFence-like framework. And this makes sense because we are only beginning to see IoT applications. There's not a whole lot of applications that we have to really be backward compatible with or worry about because this is still all emerging technology. So although porting is easy, it shows the value of how easily we can port the whatever small existing set of apps. So the real usage model would be to write apps directly with FlowFence in mind.
Any further questions? I think everybody is hungry, so thanks a lot for the presentation. And